Time to learn how to use your calculator a little more efficiently. We're going to start by graphing this function. X cubed minus 49x. Some leftovers from last time. So let's get rid of all these. X cubed. Whoops. X cubed minus 49x. I'm going to graph that. Not real impressive. Have no real sense of what's going on in this graph. I don't know if there's any other things going on between here and here. It just goes way off the screen. There's no way to tell what's going on. So this viewing window, push window, is not that great. So here's where some trial and error is going to have to come in. You're not going to know exactly what the best viewing window is right away. So you need to get comfortable changing your window settings and experimenting a little bit. I'm going to go back to my graph. I know I have a cubic function. So I know that its general shape looks like this. Now this minus 49x, maybe it goes up, there's a little hump and it comes down and then it goes back up again, but I at least know what the general shape of a cubic is, and so should you. So looking at our x-axis, I think we're pretty good. We just need to get our upper and lower a little more straightened away here. Negative 10 to 10 is not good enough. So let's make it negative 100. Let's make it positive 100. See what happens. See if that's any better. We're getting close. Now, and we can even see the general cubic there. We're getting close. But it's still not good enough. We still can't see the whole picture. Maybe 150. See what that does. There we go. Now we can see our cubic function. So if we had to sketch this graph, now we can at least see the whole picture. And we could even zoom out even more if we wanted to. Let's go negative 200, positive 200. See what that does. A little better. Now we can at least see the whole thing. So changing our window settings is a skill that you need to get comfortable doing, because some graphs are going to look real weird without the proper settings. And just relying on your calculator, zoom in, zoom out, and all these other things don't always make the best choice, because they change both x and y. This problem, we only needed to change the y. Our x-axis settings were good. Negative 10 to 10, that was good. We just needed to change the y settings. So we had to do that on our own. So sketch the graph. Well, there it is. I can now go back to my picture here. It's going to do something like this. Like so. There's a sketch. And I have to understand that my y-axis is going to be fairly large. My x-axis, fairly small, negative 10 to positive 10. Y-axis, negative 200 to positive 200. Let's go on to this one. Sketch the graph. sine 50x. I know it's a sine function, so it's going to look kind of wavy, I think. But I need a little more detail than that. So back to my trusty calculator. By the way, whenever we graph trig functions in calculus, in fact, anytime trig functions arise in calculus, 99.999999% of the time, you need to be in radians. Your days of using degrees for trig function are pretty much over unless you are dealing specifically with a triangle. And even then, it's going to be to your benefit to switch those degrees into radians most of the time. We need to be in radians when we deal with trig functions. So set your calculator radians. Sine 50x. And I'm going to go zoom trig to get a nice trig graph here. Something bothers me about this graph. I don't like how all these look like little fuzzy things here. And that's not what I expect to see. If I just do sine x, I get a nice smooth curve. If I put the 50 back in, I'm getting all these little fringy things here, and that's not good. So I need to play with this graph a little bit. Let me change the window. Okay. Let me go negative, let's say 3 pi, scratch that, negative 4 pi, to positive 4 pi, I'll leave my scale there. Let's close it up a little bit. Let's not go so high on the y-axis. Let's do that and see what happens. Oh boy. That's even worse. But now we can see that since we've zoomed in a little bit, we get some more detail. All right. Let me go, I'm going to forget the pi values and just go negative 10, positive 10. See what happens there. Oh my. That's even worse. How about negative 9, positive 9? That looks nice and artistic, but still worse. How about negative 6, positive 6? Now I'm perplexed. I went from just really weird shapes to now a nice smooth curve. This is why we cannot 100% rely on your calculator. Let's go back to this function for a moment. Sine 50x. And review a little bit of our trig that hopefully we have not forgotten. B is 50. A B value of 50 means very, very, very close together waves. Very, very close together. Also remember, B equals 2 pi over the period. And the period is 2 pi over B. So I can calculate the period is 2 pi over 50. Very, very, very small value. In fact, 2 pi divided by 50 means we have a period length of approximately 0.126. That's a very, very small period. One entire cycle of this sine graph needs less than 13 hundredths of space on the x-axis. Now we can use that, though, to help us find this graph. Our calculator was trying too hard to get all that data shoved in such a large area. This is too big of an area. So it's trying to fill all that space. If I go back to -9, +9, well, we got this graph. That's not a sine graph. We should know that that is not a sine graph. Our x-axis is zoomed too far out. And our calculator is trying to fill all that space. So the solution to that is use this period to help us with our x-axis. Let's go 0.25. That's just over 2 periods, and I should make that negative. Negative 0.25. What do you mean syntax? Oh, because I pushed minus, I didn't push negative. That would explain it. 0.25. And I'm going to make the scale 2/10. So every tick mark on the x-axis will be, no, that's too much. 0 to 200ths. There we go. Now we get a nice, smooth sine graph to scale. Now we get our nice, smooth graph. We have to understand that our calculator is so zoomed in on the x-axis that that's what we need to get this nice picture. All those really weird things before, that's a bad sign. Again, we need to know what a sine graph looks like in general in order to determine if our calculator is really telling us the truth or not. And we saw that those first few attempts were not. So we had to dig in a little closer. What's the actual period? We had to zoom in so far without changing our y-axis that we eventually got down to this value. And I don't know if that's actually what. Oh. Yeah, that's pretty close to 0.126. So from here to here, that's 0.126 units of measurement. We had to zoom far, far in. When we did our initial scale of -12 to 12, -9 to 9, and so on, we were trying to show so many of these that the calculator was trying to fill that space nicely, and it couldn't. So use your knowledge of certain functions to help find appropriate values. Here's another trig graph. Now this one, we might not have a good idea of. We see a sine of x, we see a cosine of x, and they're being added together. We also see a potential red flag. This a value is extremely small. This is extremely big. It's bigger than the last one. So when we go to punch this in, sine x plus 1/100th, 0.01, cosine, 100 x, close. I'm going to use my standard trig window, and I'm very skeptical that this is the actual graph. I'm not buying it. Because again, it looks like there's a little tiny bit of bump there, and I know that there is no way this part is being shown properly. No way. So we need to go really, really small again. How small? No, we have to guess. Let me go to negative 0.2, positive 0.2, and 0.02. Let's see what this does. That didn't do a whole lot. I'm not getting any detail here, which tells me my y-axis is too big. Let's go down -1, +1, and let's make our scale 0.1. Okay, that's a little better. That's a little better. Let's go even smaller. -0.1, +0.1, and I'll make that 0.01. Now we see some detail. We see these little steps. But it's on a very small scale. So we almost need two graphs here. This is an extremely small scale. Extremely small scale. So how do we graph this function? Well, we sort of have a nice smooth curve. Let me go back to my original one here. It almost looks like a nice smooth curve. However, when we zoom in, we get, let me just go back to a zoomed in version. I believe this was -0.1, +0.1, 0.02. I think this was -0.1 as well, +0.1. I think I went 0.1 for that. We get these little steps almost. So something like this. And this part is what's going on in that section of the graph. So as we zoom into this graph, what looks like a smooth curve, we're actually seeing this, all these little blips. It's just that we have two completely opposite functions here. This is a large scale. This is a very, very, very tiny scale that as a whole, it looks nice and smooth. When you look at it more closely, it's these little mini rises and falls. So one graph almost isn't enough to show the whole picture. One final thing that we can do with our graphing. Oh, before we move on, the moral of this story: don't always trust your graphing calculator the first time. Make sure you have a sense of what the function is. You should know, looking at the equation, what type of graph kind of sort of to expect, whether it's a rational or a quadratic or a sinusoidal, etc. So you have somewhat of an idea of the type of picture you're going to get, and then use your window settings to help you narrow down that type of picture. One final thing we can do with our graphing calculator is solve equations that aren't easily solved. There is no trig property, at least that I know of, that allows me to solve this equation. Sure, I could take the inverse cosine of both sides, but what's the inverse cosine of x squared? Don't know. Can't factor anything, can't use a nice little substitution or an identity. My only real option is to graph and see where they cross. Cosine x, everything else can go away, and x, whoops, wrong order, x squared. I'm going to change my window back to, I'll do zoom trig, number 7 here. And I see 2 points of intersection. Let me zoom in on those. Now I can use my zoom tool. Zoom in on this spot right here. This is pretty much how we can solve this equation. Second, the calc, and I want 0. We know what zeros are. Calculator asks me, what's your first function? Actually, I hit the wrong one. I'm sorry. Let's go back to second calc. Intersect. I want intersect. Number 5. What's your first curve? It's right there. Enter. What's your second curve? Right here. Enter. I have to tell the calculator, what 2 things am I solving for? What 2 things do I want intersecting? Now guess, where do you think they intersect? I think they intersect right here. And I can be off. I can guess there. I can guess there. I don't have to be exact. I just have to be in the neighborhood. This is a technique, by the way, we're going to get into later on in calculus, because this uses a calculus property called Newton's method to find things like this. And one of our basic calculus topics leads to Newton's method. So you'll learn how your calculator actually comes up with these things. Enter. And there's my intersection. At x equals negative, well, to the nearest hundredth, negative 0.82 approximately. Now that's one intersection. There were 2. Let me go back to my graph here. Zoom. Zoom in. over to this area where I see that cross. And I'll do the same process. Calc, intersect, first curve, second curve, and I think they intersect there. That process still finds the intersection positive 0.82 approximately. Using your calculator to solve more complex equations.